So our next speaker is Dr. Carli Roulston, who is a neuroscientist at the Florey, specializing in research into mechanisms involved in brain injury and repair following ischemic stroke. Her lab investigates new strategies that rescue, restore the neurovascular unit to improve long-term functional outcomes for stroke. She's speaking on targeting the neurovascular unit to reduce secondary injury and restore lost functions after ischemic stroke. Carli?
Thanks, Ashley. Thank you, Amy, for inviting me to speak today. I actually am a stroke researcher for a long time, but mostly associated with recovery of motor functions. So it wasn't until I recently came to the Florey and I met with Amy and I started talking with Amy that I realised that some of the work that I'd been doing in that space might also be relevant for cognition and cognitive decline in stroke. So I'm going to skip this because I think everybody knows the importance of stroke. I'm going to go straight into my model. I'm going to need this. So I use the Endothelin-1 model of middle cerebral artery vasoconstriction. So this is a model of stroke that's performed in a fully conscious rat. Basically, we implant a stereotaxic guide cannula to sit above the middle cerebral artery 7 days prior to stroke induction. And then on the day of stroke, we infuse endothelin-1, the potent vasoconstrictor, onto the middle cerebral artery in the conscious rat. And is there a way? Oh yes, there is a way. And I've just got this little video here to show you what I'm talking about. So basically, during stroke induction, the animals display a number of behavioural changes that are indicative of stroke that allow us to give an indication of what sort of stroke the animal's having, whether it's small, moderate or large. One of the first things that we see is the animals often raise and clench their contralateral forepaw. They often start bobbing into the contralateral direction before then they start fully turning and circling in the contralateral direction. So when we get that sort of response, we know that we've got a moderate stroke. But after that, often the animals will start to ipsilateral turn and drag their contralateral forepaw. They'll start chin weaving, salivating, teeth chattering and biting. They might undergo seizures. And so that's when we get up into a really severe stroke. So we've been looking at how we can use these behavioural changes during the conscious stroke to predict and stratify animals to treatment based on stroke severity. And when I'm speaking stroke severity, in this case I'm talking about functional decline and infarct progression. And what we've done is we've correlated changes in function and changes with infarct volume with our predictive outcome score. And if Leonard's in the room, I'm a little bit reluctant to use that word predictive, but that's what we've called it. And in so doing, we've progressed to have a look at multiple treatments, both in the neuroprotective space, but also in the recovery space. And it's the recovery space that I want to talk about today. In particular, I'm interested in the biological response to stroke. So what happens to multiple cells as the brain becomes damaged? And in particular, how does this affect secondary injury progression? So we've been looking at angiogenesis and using various immunohistomarkers, chemical markers to look at new blood vessel growth. And what we find is that we get quite significant increase in angiogenesis in the penumbra after stroke, but also across the core. And what we have done is we've counted this response using stereological tools and correlated it back with the size of the infarct at various time points to show that as the stroke severity increases, so does the angiogenic response. So here we have a system that we've got more damage, but we've also got more remodeling occurring. And so this kind of fits in with the idea that it's not necessarily the degree of damage that somebody has that determines their ability to recover. The same we've done with neurogenesis, and we've looked at increasing neurogenic responses in terms of increased stroke severity. And what we find is that in particular, we do still get increased double cortin expression in the subventricular zone after stroke. and that we get peak angiogenesis occurring at 7 days, and that this correlates nicely with increased stroke severity. So again, it doesn't matter if you're having a small stroke or a large stroke, you are still getting a neurogenic response. Interestingly, what we found when we were doing this study was that many of the cells that were dividing within the subventricular zone were also labelled for GFAP and nestin, with an indication that many of these cells were becoming radioglial cells. And we actually followed their migration and found that these cells incorporated into the glial scar. And when we have a look to see what's going on in terms of astrogliosis at 14 days after stroke, we find that in the normal brain, astrocytes, and I'd like to point this out, hopefully. Star, yep. So astrocytes here can be seen to form long extended processes throughout the brain, and in many cases they're coupled around blood vessels. And that's what astrocytes do. Astrocytes help form the blood-brain barrier, they formed end-feet connections with blood vessels, and they act as communicators between blood vessels and neurons. But then, after stroke, what we find is that these astrocytes change significantly. So basically they retract their processes, they enlarge, they actually proliferate, they group together, they have overlapping diffuse morphology, and they form the glial scar. Now, interestingly, as stroke severity increases, the number of trophic astrocytes decrease and the number of scar-forming astrocytes increase. And so when we're looking at inflammatory responses in the brain after stroke, we've also studied microglia. And so in the non-damaged brain, microglia take on a nice quiescent phenotype, characterised by small cell bodies, lots of ramified processes. But following injury, both within the penumbra and the cortex, we find that microglia are upregulated and they take on this phagocytic phenotype and invade, particularly the core infarct. So we've again correlated this back with stroke severity with more intense microglial response in larger strokes. And I should clarify that it's not just because it's a bigger stroke that there's more microglia. It's an actual digital biopsy that we use, so it's the greater number of cells within the same space. So it's a density response rather than just more cells. So years ago, we actually looked at microglia after stroke to basically try and assess, I was actually assessing minocycline during my PhD and the effects of minocycline on microglia in CNS injuries. And so what we found was that microglia become activated in the non-damaged brain. I'm in front of myself. They become activated in the non-damaged brain, as can be seen here and here and here. And they migrate through the corpus callosum so as to end up in the damaged brain. So what we see is just this clear migratory path of microglia throughout the white matter to end up into the infarct regions. Now, recently, we've gone back and had a look at what's going on in terms of that pathway across from the non-damaged brain to the damaged brain, and in particular starting to have a look at what's going on in the hippocampus. And we had a vacation student over summer go through a lot of my tissue excess to come up with this data. What we're finding is that as we're churning through a lot of our tissue excess, we're finding that microglia are actually upregulated in the dendrite gyrus as early as 24 hours after stroke. And this effect intensifies, as you can see here, as the microglia go from the contralateral brain into the ipsilateral brain, we get more numbers of microglia activated. And then by 7 days, it looks like this. So what does this mean? And just to remind you, in this model of stroke, we don't get immediate acute injury in the hippocampus. So bearing that in mind, I've gone back and had a look at some of our NUN staining. Now, NUN is a stain for neurons. in some of the work that we did 28 days after stroke. And as you can see, we've got a significant, oops, that's not what I wanted to do. We've got a significant loss of neurons both in the cortex and in regions of the striatum. But interestingly, you can see the difference between the left hemisphere and the right hemisphere. So we've got right hemisphere atrophy, and this is in all of the animals that I've seen at this time point. But we've actually got what looks to be hippocampal hypertrophy. And then when we go and have a look at what's going on at a high magnification, there's clear loss of neurons in the CA1 and the CA3 regions. So the question that we would next ask is, what are microglia contributing to in terms of long-term secondary injury in the hippocampus? And so that would be the obvious next step. But before doing that, we decided to look at correlations between changes in spontaneous recovery after stroke to changes in biological response. And so a postdoc in my lab 10 years ago correlated changes in functional loss as detected through neuroscores and through the hemi-neglect test, the sticky label test. And she found that common time frame of spontaneous recovery was between 7 and 14 days. But unfortunately, no further recovery was observed beyond that time point. So when we went back and actually had a look at all of our biological data across these timeframes, we actually found that probably what was the most significant effect here was this peak microglial event that was occurring at 7 days, and then a drop in microglial responses by 14 days, and spontaneous recovery. But as astrocytes changed their morphology and created this glial scar, we found that that scar started to expand out into the non-damaged brain, and that this correlated with a cessation of spontaneous recovery. So we partnered with Professor Phil Beard, who at the time was working on astrocyte cultures, and he had been using the Rho kinase inhibitor Fasudil to look at astrocyte responses in relation to a treatment effect. Now, when astrocytes are grown in cultures, they actually take on an activated phenotype and morphology, and when I'm talking about phenotype, I'm talking protein and gene expression according to an activated cell. So when these cells are treated with Fasudil, by 24 hours, their whole phenotype has changed, and that they've reverted back into what's considered a growth-promoting trophic phenotype that includes improved regulation of glutamate transporter gene expressions and increases in BDNF. So we've taken Fasudil now and put it into our animal model of stroke to see whether or not we could get a similar effect. And what we found was that we wanted to test the effects of Fasudil on astrocyte responses, inflammation, but in particular as a treatment to promote recovery. So what we did was we allowed the infarct to mature by 3 days and then started our treatment. And with treatment, you get a decrease in neuroscores by 28 days with Fasudil. But importantly, when you use the cylinder test, and the cylinder test is a great test to use for long-term loss of function in the stroke-affected forepaw, we get continuous decline in our vehicle-treated animals, but we get a complete reversion of this effect with treatment with Fasudil. And when we have a look at what's going on at a biological level, we find that in our vehicle-treated animals, we've got this big scar formation process occurring with lots of activation of astrocytes expanding out into the non-damaged brain. But the rats treated with Fasudil did not display the intensity of this scar, nor did it actually traverse out into the non-damaged brain. So when we have a look at this at a high level, and particularly in terms of co-localization with blood vessels, we find that typically in our vehicle-treated animals, the astrocytes detach from blood vessels, and in our animals treated with Fasudil, it looks much better on my screen. Just trust me. That's a shame. They've actually, this is terrible. All right, I'll use this one here. You can see that the astrocytes have retained their end-feet coupling, their association with blood vessels. And so what we wanted to do is understand this on a more of a global scale. So in terms of the translational effects of this in related to protein signalling, and collaborating with my friends from biochemistry, we've actually done a whole mass spectrometry and proteomics assessment of I think we identified 1,800 proteins of interest that were affected by stroke, of which 800 proteins had a twofold change differential expression with treatment with Fasudil. So we're currently going through all of these at the moment to try and determine what this data means and try and relate it back to obviously our functional and biological effects. Firstly, I want to say that after stroke, many proteins are downregulated, and Fasudil restores these. And many proteins are upregulated, and Fasudil attenuates this. So what might be of more interest to the current audience is when we put many of our hand-selected proteins of interest into IPA analysis, we find that the types of proteins that are regulated positively by Fasudil include synapsins that are involved in synaptogenesis and axonogenesis, some of the neuroplastins which are involved in cell-to-cell interactions, and pure alpha, which is involved in microtubule formation and cognition. But what's more really interesting here is that we get many of the inflammatory associated proteins downregulated with Fasudil treatment, including APP, including CLU, catalase, and somewhere on here is also ApoE, which I failed to point out in the actual presentation when I was preparing the presentation, but I think might be interesting to this audience and moving forward to look at the effects of Fasudil on cognition. So I'd just like to thank everybody in my team who is involved. Obviously, I'm all about multiple cells, not just one. I think when it comes to tackling neurological disease, we're not going to do it just through one protein, one pathway, and one cell. So I'd like to challenge everybody to think about multiple cell interactions to restore the injured brain. So thank you.
Thank you, Carli. Questions afterwards?